Okay, welcome. I wanted to give you guys a little bit more practice with dynamic programming. And I know, like, if you just see the neoclassical growth model, even if this is something that is your forte and you're really, really good at math and you learn it really quickly, seeing just like one model with this stuff may not really be enough to get it to set in. Might be something you need to play around with it a little bit more. And, if you just practice the same model over and over and over again, you're getting really good at solving out that model, but you have no guarantee that you're actually getting the process rather than just memorizing the math. So I figure if I can give you guys a little bit more math to play with, to give you some extra practice, maybe then, we can kind of parse out how well we're getting this. And, if there are any deficiencies that need to be addressed. Because I do know that this can be kind of hard, and I don't want to leave you guys kind of to the wayside. I don't want to leave you guys to the wolves here. Well, I guess enough me rambling on and on and on. Let's do some recap on this stuff, right? So when you have your optimization problem that you need to solve, and you set up a Bellman equation, it's always going to look like what you see in equation 1. It's going to be v of kt equals the natural log of ct plus beta times v of kt plus 1. And then c sub t is set equal to that resource constraint that you have with all the endogenous variables substituted into it. So it doesn't have to be this simple, though. Now you're probably going like, what the hell? This simple? This isn't simple at all. What I mean by this simple is like with this few inputs or this few arguments in the v function, because here it's v of kt, but you don't just have to have capital. You can have other choice variables. You can also have more in the utility function, so you don't have to have just u of consumption. It can be u of consumption and money holdings, right? So you could have like u of ct and mt equals the natural log of ct plus gamma times the natural log of mt if you wanted to have money in the utility function. Now, if you've taken intermediate micro and you've probably already done some calculus with the utility maximization stuff, you probably did something like with Lagrange multipliers. Another way that you could do it is substitution. So you would end up substituting the constraint into one of the choice variables that you have there. This really isn't any different from doing that. But if, regardless of how many inputs you have in the utility function, you would only ever substitute the constraint in for c sub t, and you would leave m sub t alone. So m sub t would always be there. And if you had a constraint, say with money and bond holdings, and it would look like c sub t equals at times kt to the alpha, which is production, right? Minus kt plus 1 minus delta kt, that's investment, minus 1 plus the real interest rate to the negative 1 times bt plus 1 plus bt. That is the flow of bonds over time. And it is discounted for the future. So the future value of bonds is discounted to give us a present value of that. That's why I've got 1 plus the real interest rate to the negative 1, or 1 over 1 plus the real interest rate. And then you have minus 1 plus pi t times mt plus 1. Pi t is inflation. So it's, again, discounting the present value of future money holdings for the rate of inflation to make it, like, to tell us what tomorrow's money holdings would be worth today, plus mt, which is today's money holdings. So we've got more variables in the constraint, meaning there are more choices for us to make, right? Initially, it was just, do you want to hold more capital or do you want to consume today? Now, it's, do you want to hold more capital? Do you want to hold more bonds? Do you want to hold more money? Or do you want to consume today? So you're getting more options, more choices, more alternatives for consuming. And you would make your decision based on your preferences and the rate of inflation, the real interest rate, and the return on capital. So, if we had money in the utility function, now actually, why would we have money in the utility function? That's probably a good question to be asking ourselves here. The reason we'd have money in the utility function would be if you derive utility from having money in savings. That's the basic idea. So the more you've got in savings, the more utility you would have. You'd be happier because if you've got money in savings, then in the event you should ever need money, so your car breaks down, you need either a new one or you need to get it repaired, or your cat gets really, really sick and she needs all sorts of crazy treatments to keep her alive over the next couple of months. Having money in the savings account would have been, would be really nice. It's going to help you out. And you would derive utility from having money in your savings account. There's actually a whole article by Milton Friedman that I think we're going to read later on in the semester. For any of you that have taken my money in banking course that are taking it this semester, it's actually required reading. It's already been required reading. Really interesting stuff. But anyways, if we have this utility function, so we've got this utility function right here, and it's being maximized subject to this constraint here. Well, the Bellman equation would look like this. We'd have V of KT, BT, and MT because we're choosing capital, bonds, and money. And then the thing that we'd be choosing as an alternative to these three would be consumption, right? So you'd have consumption and then these three guys here. So V of KT, BT, and MT equals the natural log of CT plus gamma times the natural log of MT plus beta times V of KT plus 1, BT plus 1, and MT plus 1. Now, point that I want to make here is when you're like, okay, how many first order conditions am I going to need to get here? The number of first order conditions you will need to get, where you take your derivative and set it equal to 0, that will be equal to the number of arguments in that V function. So for V of KT, you had one first order condition. Now you needed an additional derivative, which then updated the time subscripts so you could understand what partial of V of KT plus 1 with respect to KT plus 1 is, right? But for the first order condition, derivative set equal to 0. For V of just KT, that's one derivative. So the total number of derivatives that you need for equation 1 would be 2. The total number of derivatives you would need for the Bellman equation at the bottom, V of KT, BT, and MT, would be how many? Be 6, right? Because you need 3 first order conditions and then 3 derivatives with respect to KT, BT, and MT, and then you update those derivatives by 1 period. So the thing is, the process is still the same. There's more stuff to do, but the process is still the same. So your Bellman equation is always going to be like V of something equals the natural log of beta times, or the natural log of CT plus beta times V of your stuff, right? Here it's just KT, but we saw KT, BT, and MT in the previous example. Now your constraint's always going to be CT equals stuff, and that's going to be the resource constraint with all of those endogenous variables substituted in there. So you'd have like output, investment, your flow of bonds, and your flow of money. You can either substitute that in for CT in your Bellman equation, or you can keep C sub t in there. But if you do that, you're going to need to multiply the derivative of marginal utility, 1 over CT, the derivative of utility, or marginal utility, which was 1 over CT. You need to multiply that by the derivative of the constraint with respect to the variable you're differentiating V of arguments with. So if it's for capital, you'd have the derivative, the natural log of CT, with respect to CT. It'd be 1 over CT. Well, then you got your capital, right? -1. So once you have that Bellman equation, right? Once you've set your Bellman equation up, it's partial V of KT with respect to KT plus 1 equals 1 over CT times -1 plus beta times the partial of V of KT plus 1 with respect to KT plus 1. Set that equal to 0. That's that first order condition. So that's the first derivative that we had to take with the neoclassical growth model. You then need to take the derivative of V of KT with respect to KT, right? Because here, the time subscripts don't match. You got KT and KT plus 1, but here, the time subscripts do match. So you can't just go like, all right, well, I got this and I can update it or something. You can't, because the time subscripts here will never match up. So you got to take a derivative where they do match up and then just update the t subscripts by one period. So when you do that, any t subscript you see becomes t plus 1. But remember, that derivative isn't set equal to 0, because you need that new derivative, that partial v of kt plus 1 with respect to kt plus 1. You need to plug that into this right here for the first order condition. And then you move that 1 over ct to the other side of the equation, and boom. Bada bing, bada boom, you've got your Euler equation for capital. Okay, so here's what we're going to do. We're going to walk through another example. We're going to do the utility function we saw from the neoclassical growth model, so it's just the natural log of CT. And we have a constraint that is mostly the same, except I have bonds in here. So it's not just capital holdings, it's also bond holdings. And what is a bond exactly? Well, a bond is really a promise to pay money back. So if, say, I need to borrow money, I'll write a piece of paper saying, let me borrow $1,000. I will sell you this piece of paper for $1,000. Now, that piece of paper is worth $1,000 in the future plus some interest. I repay that $1,000, say, tomorrow, with a little bit of interest attached to it. That's a bond. So if you want to buy a bond, well, you got to give somebody your money now. But in this case, it's a one-period bond. So in the next period, I get my money back plus a little bit of interest, that 1 plus the real interest rate, 1 plus R. So with this constraint and this utility function, all right, I've only got one input from my utility function. So that first period thing we're looking at is just going to be CT, right? The Bellman equation is V of KT and BT, because I've got two choice variables now. I'm choosing between capital and bonds. That's equal to the natural log of consumption plus beta times V of KT plus 1 and BT plus 1. And you want to choose capital, KT plus 1, and bonds, BT plus 1. So bonds and capital work the same way. You chose B sub t yesterday, but you can choose B sub t plus 1 today. So KT plus 1 and BT plus 1 are your choice variables. KT and BT are your state variables. So we formulate our Bellman equation by just taking that constraint that we have right here, right? Because we got the natural log of CT, but CT is equal to all this stuff, right? Originally, it was just output minus investment, but now it's output minus investment minus bond holdings. So I just take what's on the right-hand side of this equation here, and I plug that in for consumption, and that gives me this right here. Excuse me. So I've got V of KT and BT equals the natural log of AT times KT to the alpha minus KT plus 1 plus 1 minus delta KT minus 1 plus the real interest rate to the negative 1, or 1 over 1 plus the real interest rate, times BT plus 1 plus BT plus beta times V of KT plus 1 and BT plus 1. This is my Bellman equation in this sense. Now, I got to get two first-order conditions. I got to get one for capital, and I got to get one for bonds. Now, I've seen the one for capital already, and it's not going to change because this constraint is additively separable. So regardless of how much crap I'm adding in there, if I'm just adding it and I'm not multiplying anything new to capital, when I take that partial derivative, it's going to give me the exact same first derivative as what I would have for the neoclassical growth model with just capital in there. Okay, so I'm doing it with respect to capital first. So it's the partial of V of KT and BT with respect to KT plus 1 equals negative 1 over that constraint, which is also CT. So it's negative 1 over CT, really, plus beta times the partial of V of KT plus 1 and BT plus 1 with respect to KT plus 1. And we set that equal to 0. The bond one, let's look at the bond first order condition. It's the partial of V of KT and BT with respect to BT plus 1. Now, when I look through this constraint, what do I have? Well, when I take the derivative of this guy right here, with respect to bt plus 1, this first term, it's 1 over all this stuff, right? 1 over ct, times the derivative of this inside, this constraint with respect to bt plus 1. Well, this isn't a bt plus 1, so this differentiates to 0. This isn't a bt plus 1, nor is this a bt plus 1. So this and this differentiate to 0. This isn't a bt plus 1, so this differentiates to 0. So really that just leaves me this 1 plus the real interest rate to the negative 1, or 1 over plus the real interest rate, they're the same thing, times bt plus 1. And what would the derivative of this with respect to bt plus 1 be? Well, that bt plus 1 would differentiate to 1. So it's really just negative 1 plus the real interest rate to the negative 1 power. And that's this right here. So it's negative 1 plus the real interest rate to the power negative 1 over consumption plus beta times the partial of v of kt plus 1 and bt plus 1 with respect to bt plus 1, and that's equal to 0. So I did 1 for capital and 1 for bonds. Shouldn't be too terrible, right? Maybe this is a little bit simpler. That's easier to look at. Okay. Negative 1 over ct plus beta times partial v of kt plus 1 bt plus 1 with respect to kt plus 1 equals 0. And I've got 1 over ct times 1 plus the real interest rate to the negative 1 times negative 1 plus beta times the partial of v of kt plus 1 and bt plus 1 with respect to bt plus 1. And that's equal to 0. All right, so now we need to know what this is, this partial v of kt plus 1, bt plus 1 with respect to kt plus 1, and the partial of v with respect to bt plus 1. But remember, these t subscripts don't align, right? The bt and kt and kt plus 1, and the bt and the bt plus 1, they're not aligning here. So we need to get derivatives that do align. And how do we do that? Well, we go back to our Bellman equation, right? The first thing that we had, we go back to this guy right here, and instead of taking the derivative with respect to bt plus 1 and kt plus 1, we take the derivative with respect to bt and kt. So the derivative with respect to kt is the same as what we saw with the neoclassical growth model. It's the nice thing about these linear constraints. It's generally going to be unchanged with respect to capital. So the partial of v with respect to kt is 1 over ct times alpha times at times kt to the alpha minus 1 plus 1 minus delta. Cool. Update 1 period. You get this. We've seen this before. 1 over ct plus 1 times alpha times at plus 1 times kt plus 1 to the alpha minus 1 plus 1 minus delta. All right, take the right-hand side of equation 9, which is the derivative updated 1 period, and I plug that into equation 7, and that gives me this right here. So this is my Euler equation for capital. We've seen this before, right? This is exactly what you saw with the neoclassical growth model. All right, well, that's not too terrible, is it? I mean, it's the same thing over again. All right, I'm going to save equation 11, though, for a couple of minutes. We're going to get back to this, so keep that in your back pocket. Because now we got to do the same thing for bonds, right? We need the derivative of v with respect to bt plus 1. So what do? Well, I take the derivative of v of kt and bt with respect to bt. So again, with this right here, right, I need this. This showed up in my first order condition for bonds. This is right here. I need this. So I go back to my Bellman equation. I go back to this guy right here, equation 4. And I take the derivative of this guy with respect to b sub t. Well, there's only one b sub t, and it's right here, and it's not being multiplied by anything. So literally the derivative of v of kt and bt with respect to bt is 1 over ct. It's just marginal utility of consumption. That's not too bad, right? Update at one period, 1 over ct plus 1. Cool. So I take the right-hand side of that and I plug it into equation 7, which is my first order condition for bonds. It gives me this right here. 1 over ct times 1 over 1 plus the real interest rate plus beta times 1 over ct plus 1 equals 0. Right? I could move 1 over ct times 1 over 1 plus the real interest rate to the other side. That gives me this. And then what I can do is I can multiply both sides by 1 plus the real interest rate, and that gives me 1 over ct equals beta times 1 over ct plus 1 times 1 plus the real interest rate. Now, does that look familiar? Think back to like chapter, I think it was chapter 5. This is listed as chapter 5 here. This is an error on my part. But think back to like the actual chapter 5 that we had. It was like the dynamic optimization stuff. Remember the Euler equation in that case? It was actually what you see in equation 15. So we've got two Euler equations here. We've got equation 16, which is the Euler equation for capital, and I've got equation 17, which is the Euler equation for bonds. Now, here's the cool thing. Look at equation 16 and see if you can rewrite what's in pink to give you something a little closer to what you have in equation 17 in the red. Take that 1 out of the parentheses for that 1 minus delta, put that in front, and write it as 1 plus alpha times at plus 1 times kt plus 1 to the alpha minus 1 minus delta. When you write it that way, and you look at equations 16 and 17, nothing is different except what's in those parentheses, right? But here's the thing. If nothing's different except what's in those parentheses, and you've got ct and ct plus 1 and beta in each of these, then doesn't that imply that what's in pink in equation 16 and what's in red in equation 17 are equal? Therefore, in equilibrium, the real rate of return on bonds is also going to be equal to the rate of return on capital. How cool is that? Why would that be? Well, it's the real interest rate, not the nominal interest rate. The nominal interest rate is a little different. The real interest rate, you can think of it as the real rate that you get, or the rate of return you get for like capital. So the rate of return on bonds, the real rate of return on bonds, and the rate of return on capital in equilibrium are the same thing. So that's just kind of interesting. Neat little takeaway there. Here's some more takeaways. For each variable in, say, v of dot, where dot is your set of arguments, you'll always have two derivatives. The first is that first order condition. You take that derivative of v of whatever your arguments are with respect to the argument in period t plus 1 and set that equal to 0. Now that gives you mismatched time subscripts. So you need matching time subscripts. So you take another derivative of, in this case, v of kt and bt with respect to bt, or kt, I guess, and you update the time subscripts by one period. This gives you matching time subscripts. That's what we want. And then you use the updated time subscripts derivative to plug into that first order condition, and that will give you your Euler equations. And the Euler equations give you the optimal time path for each variable. First, we learned about it with capital, and then, sort of because of that, like backing everything out, we get it through consumption as well. The Euler equation for bonds gives you the optimal time path for bonds, kind of like in terms of consumption. Both of them are telling us the optimal way to use our resources each period. And because this is a dynamic problem, and the Euler equation is dynamic because it's got t and t plus 1 subscripts, it's got values over different time periods, hence dynamic, it's telling us how to use our resources each period and over time. So you're going to want to practice this like a lot, but it does become second nature, I promise you. This is not, it seems like a lot, yes, as you're learning it, but as you learn it, you start to realize, hey, this really isn't all that bad. Because the idea is the Bellman equation gives us our Euler equations that we need to solve the models out. And then the Euler equations tell us the optimal intertemporal flow of resources for the representative agent through various instruments, right? You'd have capital, bonds, money, etc. And these equations tell us how the household is behaving optimally over time. It's giving us an intertemporal link. It gives us a link between today and tomorrow. So here's what I want you to work on your own. And this isn't like for a grade or anything like that. It's just something to give you a little extra practice. You've got the utility, natural log of CT. And you have a constraint with capital, bonds, and money, with pi t as the rate of inflation. The Bellman equation here would be V of KT, BT, and MT equals the natural log of CT plus beta times V of KT plus 1, BT plus 1, and MT plus 1. And here's what I want you to do. I want you to get the first order conditions for capital, bonds, and money. I want you to get the Euler equations for capital, bonds, and money. And in, I don't know, about a week or so, maybe, sometime next week, I'll post a video with the answers to it. But I want you to work on it on your own first. And I want you to see what you get. And if you think you might be a little stuck, feel free to reach out to me. I'm always happy to help. I'm always here to answer questions that you might have. Now, in case you don't know where to get started, let me give you a hint. Equation 18 isn't that different from, where are we here? Equation 4, except it's got the flow of money in there as well. And remember, the flow of money is additively separable. It's a linear constraint still, even with money. You got capital, bonds, and money in here. Equation 4, you just got capital and bonds, right? Now, when we added bonds in there, did the Euler equation for capital look any different? The answer is no. The Euler equation for capital was equation 11. Right? We added bonds in there, but the Euler equation for capital is the same as if bonds weren't in there. And that's because we've got the additively separable constraint. So if the Euler equation for capital isn't any different, even when we have bonds in our initial constraint, then perhaps, just maybe, it won't be any different when we have money in there as well. And similarly, when we do have money in there as well, if the Euler equation for capital won't be any different, then the Euler equation for bonds, it stands to reason, wouldn't be any different either, because again, it's additively separable. So if the Euler equation for capital and bonds aren't going to be any different, then you've actually got 2/3 of the Euler equations that you need. You just need the one for money. So try to get the one for money through the same process you used for capital and bonds. If you can do that, well then, hey, you're golden. You're in excellent shape, and you're just that much closer to really being able to master what this stuff is. So I'm going to leave it here. I'm going to leave it here because this is the end of the slideshow presentation that I have produced for you. And in leaving it here, I now leave you with this problem. So feel free to work on it. Take a couple of days. Maybe you need a couple days. Maybe you don't. Maybe you need my help. Maybe you don't. If you need my help, please, of course, reach out. Happy to help. And we'll see where we get in a couple of days. And then I'll give you guys the answer. And hopefully the answer I have is the same thing as the answer that you've got. And in the meantime, have a great weekend. I'm sure actually most of you will be watching this on Monday. I wouldn't be watching this on the weekend if I were you. I'd be out like having fun with my friends or something. But if you want to do this is fun for you. It was fun for me. Then feel free to do it on the weekend too. But either way, I'll give you guys until the middle of next week. So I don't know, 14th or 15th, I'll probably have something up for you guys to look at and compare your answers to. And in the meantime, enjoy yourselves. And of course, there will be another video coming out this coming Tuesday. So thank you for watching and take care.